All right. Hello, everyone. Welcome this afternoon to our Metallurgy and Manufacturing webinar out of Battle Creek, Michigan. We're very excited to do this webinar today for you. We have two special guests all the way from Germany to show us some of their expertise in metallurgy and manufacturing. Katharina, on our right.
Nice to meet you.
She will be going through the metallurgy portion of what Picard offers. She is the head of our development in Germany. And then on my left is Sebastian.
Hello, nice to meet you.
Sebastian is a product manager, and he'll go through many designs that Picard offers. And Ben Baldwin is also with us. He's our inside sales support for the U.S., and we're excited to have him on board today.
Afternoon, folks. If you have any questions, feel free to use the raise your hand feature or type it out in the Q&A portion and we'll get to it. Thanks for coming.
And we also have Guy Alderton on the call. He's our Vice President of Sales that has really orchestrated this whole webinar today and coordinated things, and he'll be able to answer and support us as well during this webinar. It looks like everybody that registered is on the call, so we can go ahead and get started. I'll have Katharina start for us.
Thanks a lot. I will start my presentation. 1 second. Okay. Thank you, Kyle. And I will start. I'm Katharina. I'm the head of our development department, and my background is metallurgy. So I will tell you something about metallurgy and why we need it in extruders. I would like to start with the different wear zones we have in extruder. So we are starting with the feeding zone. In the feeding zone, we mainly see abrasion because we have non-melted granulates. And then it's going downstream to the melting zone, where we have very high torques and very high pressure in the extruder. What we mainly see at the kneading blocks, they often have a very heavy wear. And going further down, we have the feed zone for additives. And they're a little bit splitting up between abrasion and corrosion, depending on your additive. So if you add something like a flame retardant, you will see more corrosion. If you add something like a glass fiber or any fibers, you will see more abrasion. And the worst case is that you could see both at once. And going even further down, we have the degassing zone. At that zone, we mainly see corrosion because we have volatile components or steam that is going out. And last but not least is the discharge zone, where we often have heavy wear because we have an extremely high pressure. And sometimes even the shafts are pulled apart at this position and running against the liner. And here's a little bit summed up what we can see in an extruder for wear mechanisms, and starting with the power transmission. So a shaft that got too much torque looks like that, it breaks. We don't see that very often, but it is there from time by time. Then I really like this kneading block because you can see so heavy corrosion on it. It's an issue in many processes, and it's getting even more that we see corrosion. Abrasive wear here, like I said, in the kneading zone, we often see that, and here the shafts are really pushed apart, and you could see that there's heavy wear in the zone. And you see all the single kneading discs at the wall of the liner. And we have adhesive wear. We do not see that often, but it could happen that if one part is much softer than the other part, that you have a material transfer from one to each other. And that is then called adhesive wear. It's a cold welding. And now I will say that very often in this talk, and I really want to stick to that. So wear is always a system property. That means we have to take everything around into account. So we have the material that we are using, so our steel or whatever, where we make our elements of or our liners out. Then we have the product, what you are producing, and we have the environment. So it's a real difference whether you have your company at seaside or in the middle of the land, and everything of that counts. So you can never say a process is working at one side is working at another side the same way. And that is what is we're about. We have to take always everything into account. And now I want to go a little bit more into material and steel that we are using at Picard. Mainly we are using steels. I will show you later that we sometimes use some other materials, but this talk will be mainly about steels. And we are using 4 groups of steels for extruder parts. Starting with tool steels. Tool steels are always high grade. That means they have a lot of alloying elements. They don't have to be rust proof, but sometimes they are. They have a relatively high hardness and tensile strength, up to 70 HRC, which is very hard. And to come up to there, they have to have a high carbon content. And normally they are hardened and tempered. I will explain later what that means. And they are divided in 3 groups: cold working, hot working, and high speed steel. That only means at which temperature they could be used. Then we have stainless steels, and please, I know many people thinking stainless steels are always rust free, but that's not really true. I will show later why they can rust. But what they all have in common is that they have more than 10.5% chromium. And because of that, they build a passive layer on the surface that is protecting the steel against corrosion or acid. And there are 2 different types of stainless steel. They're the type without nickel addition. These are mostly hardenable and magnetic. We are using these steels for most applications because we need the hardness, because at the most sites we have wear and corrosion. There are very less applications where we have only corrosion. And then there are steels with a high nickel content. They are called austenitic steels. They are very hard to machine because you get relatively large, long chips by turning or milling. They have a high corrosion resistance, which is very nice. They are non-magnetic, so if you see somebody who is dealing with scrap, they have always a magnet with them to see which steel type it is. And they could not be hardened as tool steels or other stainless steels. They're hardened by through working or surface treatment. Then we have the group of construction steels. They are low carbon steels. They don't have that many alloying elements. We are using them for barrels because we don't have to have so much properties for them. They are very good weldable. That is important for us because the cooling system is welded in many cases. And they have a high toughness, so they're easy to handle. And last but not least, we have nitrided steel. These steels are used to be nitrided. That means that they get a coating with nitrogen, or maybe not a coating, but a surface treatment. This coating is extremely hard, wear resistant, and can withstand up to 500 degrees. To do so, you need nitride forming elements like chromium, aluminium, molybdenum, or vanadium. And they normally have a carbon content between 0.2 and 0.6%, so that they are hardenable. And now I want to tell you something about a process which is often used for extruder elements and which is very important for us because we get a very sophisticated material out of it. We are not doing that by ourselves, we are buying it, but I would like to explain you the process and afterwards why we get many advantages out of it. This is the HIP steels or hot isostatic pressing. And what is done? So we are starting with making a very high alloyed steel, and then the steel is made to a powder by atomization. And this means that we cool it very rapidly, make it to powder, and every powder grain you have all alloying elements in it. And due to that, you are able to make very high alloyed steel, which normally could be only casted. And afterwards, you have this powder, which every grain has a similar alloying content, and put it into a capsule. You fill this capsule, and then the powder has to be compressed, and the capsule has to be enclosed airtight, which is a lot of know-how from the HIP steel suppliers. When you get this capsule and it's closed and it's airtight, then you put it into the HIP process. That means we have very high temperatures around the melting temperature, a little bit under the melting temperature of the steel, with very high pressures, and it stays there for 8 to 12 hours. When you're ready, you remove the capsule, and then you can work with the material. As you know, we have different type of these HIP materials. So we have the one type are our liners. There we put a tube in the middle so that we don't use so much material in V8 bore. Then we have our soft core material. There we put the soft core in the middle. And we have massive or solid versions where we put the whole capsule with powder. And the advantages I would like to show you in a microscope image. So on the left side, you see a rolled steel where you can see different things. So on the one hand, you can see that they are not that pure as the HIP steel. And so here it could be starting points for breakage, especially when you have a very high alloyed steel with a brittleness. On the other hand, you can see that there's the rolling direction that can be seen on the steel. As you see, it's going from here to there. And in the HIP steel, you have very, very fine grains. You cannot see it on this image, but due to that you have not this, that you have no direction and very fine grains, you have a very homogeneous and isotropic properties of the material. Here I put a table where we compare rolled and forged steels to ESR steels and HIP steel. ESR means electro slag remelted. That means we remelt a steel and like filtering it to the slag. Therefore, it gets better properties, but the HIP steels are the only steels with isotropic properties. That means that you don't have any direction properties or not depending on the direction. The purity is getting better from rolled to forged with a moderate purity to very good purity with HIP steels. And ESR and HIP steels both have a homogeneous structure. Very special about HIP steels is that you can get especially very high carbon content, but also other alloying elements can get higher than they could at a conventional steel. We have steels with a carbon content up to 2.8% and chromium content about 25%. That's really high. But it's a cost point. So as you have seen, the HIP process is very long, and you have to do more things than a conventional process. So the material costs are higher than the rolled and forged steel. And now I want to go a little bit into detail how hardening works, but just a short section about that. When you harden the steel, you normally heat it up to hardening temperature, and then you have to quench it very fastly so that you build martensite. I will show on the next slide a little bit about the lattice, and then you are done with the scientific stuff. And afterwards, you have directly go to tempering the steel, because when you just harden it, it's normally very brittle. And with the steels with the high alloying content, they will behave like ceramics or glass. When you push them to the ground, they will break. We have different materials with different tempering steps. So the tempering depends on the one hand of the alloying contents and what we want to reach. If we have a material with a lot of retaining austenite, we have normally to do 3 tempering steps, but we have some materials where we don't need that. There we do 1 or 2 tempering steps. It really depends on the material. And we have different tempering temperatures depending on the material. We often use secondary hardeners where we build carbides by the tempering. And here's the lattice. For the hardening process, you know the carbon iron diagram. I don't want to show it here. I just want to show what is happening. So when we heat up a steel that's in the middle, we get a cubic face-centered lattice. And as we have heat in there and the atoms can move, because they have energy. Carbon finds space in the middle or at other positions in the lattice. And now there could be happening two things. When you cool down slowly, it will go back to the cubic body centered as it is before heated up, and you will have the carbon as cementite as a phase next to it. But that's not what we wanted. We want to quench it, so cool it down very rapidly. And then we have a diffusion-less transformation, and the carbon cannot go out of the lattice because it's not fast enough. And so we have a highly strained lattice. And what we are doing while tempering, on the one hand, we try to build some carbides when we do secondary hardening, but we also want that the carbon gets a little bit of energy so that it can move out of the lattice and it's not that highly strained and the stress is reduced. Now I just want to show you why a stainless steel can rust. So as I said before, it's building a passive layer. And this passive layer is built with a chromium that is free in the matrix. So chromium and dioxide build a layer, so we have chromium dioxide. When you scratch the layer, wherever, then it's broken. And normally it directly builds a new passive layer, so it's self-healing. But if you do that too often, it cannot heal anymore, and you will get rust at this point. Because the chromium has always to get by diffusion to the surface, and if you do that too often, there's not enough chromium left near the surface. And that brings me to my next point. I want to explain that we at the main or oftenly have tribocorrosion. That means the mix of abrasion and corrosion. And as you can see, here's the total loss of material in this light blue. And this consists of 4 parts. So we have the part which is only caused by corrosion. So material is vanished because of corrosive attack. And we have the part which is only abrasion. And that we could measure relatively easily, and we can do tests which simulate this, so we can forecast it. What is very hard to forecast are the other 2 parts, which are the main parts of the tribocorrosion, and that's corrosion caused by abrasion, so that you hurt the lattice and things like that. And because of that, corrosion can start. And the largest part is abrasion caused by corrosion. That means we have abrasion because the corrosive products can be removed very easily. And that comes back to my first point, that wear is always a system property. So you have to take into account everything like temperature, humidity, which products you use, and which material you have. So it's not that easy to determine which material is the best for the case. So it's a lot of discussions and understanding how a process works. And now I will come to the Picard elements and maybe a little bit more into the Picard stuff, what we are doing. So we have 3 different types of standard elements. On the one hand, we have the massive through-hardened ones, which we can make out of forged or rolled steel. So for relatively easy applications, like our 00 and nitride steel, or our 05 for corrosive attack. Then we have ESR, electroslag remelted steel. They offer sometimes a little bit better properties. And then we have our HIP through-hardened steel, which are made with the HIP process but have no soft core because of different reasons. One could be that the size does not fit, so we have not enough space here to put a soft core in it. Then we have our HIP compound, which is a PM steel with a soft core material. I will tell you on the next slide why you should choose, or why we have big advantages when we have a soft core. And then we have the HIP crest area. That is only for very special applications. If someone needs like a bearing effect, we can use them as stellite or cobalt-based material. Or if people have very corrosive environments and need a nickel material, then we can make a nickel crest that has better properties or higher hardness than the base material. Yeah, we can choose different types of material. I told you a lot about the iron alloys. I don't want to tell them again all, so we talked about that. Then we have nickel alloys like Hastelloy or Inconel, or sometimes even special applications. I will show later one special nickel application for liners. And then we have cobalt alloys, which are used, as I said, for sliding effects or for corrosion too. And here are some points why we are using soft core and why we like to use soft core. So soft core elements were developed by the OEMs for high torque machines in the 1990s. So now it's over 30 years ago. And they have the advantage that the soft core and the shaft could react very flexible to torque fluctuations. That was the main reason why they were invented. And in the case of crash, if you have a through-hardened element, the crash normally goes really through the element and it will split up into parts. If you have a soft core, we see that the crack normally stops before the soft core, so you're protecting your shaft. Moreover, if you have a very hard element and it's through hard, you can damage your shaft by put the elements on or get them off because they're much harder and they could like cut into the shaft. And for us in manufacturing, we could have a much better accuracy because we can do the broaching after the hardening. If we have a through hardened element, it's normally not possible to do the broaching afterwards. And one environmental aspect, if we have a soft core, we don't need that much of this powder, which is very expensive and where a lot of energy is put in. And I'm often asked whether the binding is good between the soft core and the material, and I have no doubt that it is because it's a diffusion bonding. That means the atoms are going from one side to the other side, as is shown here. So you have really a mix-up of atoms. Here you see the transition zone in the middle, and then you even see small transition zones where you see like going it out. And what we have done is that we made tensile tests out of a sample where we go through the bonding, and the tensile tests never break or crack in the bonding. It breaks in the hard or in the soft material. And that's a little bit how we choose which is the right material for the custom applications. So we're starting with the properties that are defined by your process. So we are seeing whether it's about strength. So for example, for shafts, or toughness. In some zones of the extruder, we are not able to put in every material because when it's very brittle, it's not the right material for this zone. We are looking on the wear behavior. So do you have abrasion or adhesion? And one point more is the corrosion resistance. Do you need corrosion resistance? Is it the most important thing or not? Then we choose a material suitable for your application. We have to have a look at the dimensions. As I said before, some diameters we can only produce in a massive version because it's too small. And last but not least, and I think that's very important, is the price. So if somebody has not that sophisticated things that we have to see or to do, then we have to use the most cheap material, the cheapest material for that application. Yeah, on the right side, you see some standard lifetimes. So we say for elements, it's approximately 1 year, but that's only overall our customers, what we experience. Sometimes you have like 8 weeks. It really depends on your process. Shafts normally reach out to the 5 years, and liners and barrels approximately for 3. And now we're coming to our portfolio, and I just would like to explain this graph very shortly. So what have we done? We have done a graph, and this is grounded on our experience, material analysis, and some tests we made, like corrosion and wear tests, and we put all this knowledge together. And this is an overview how we have seen it in the past. It's not fitting for every customer, it's just like an average. And it's divided into the light orange. These are our hip materials with a soft core. The gray ones are the conventional steels or ESR melted steels. And the dark orange ones are our crest welded or crest hip steel, or not steels, materials in this case, because they are mainly no steels. And a material which fits very well for corrosion and abrasion is the material 25. It's a good mixture. If you have mainly abrasive wear, we would recommend material 15, or for some zones, material pH, but pH has a problem, it could be very brittle. But pH has one advantage, it has a relatively high cobalt content, and therefore it is heat resistant. For some customers, especially in the polyolefin industry, our material 00 is a very good choice. It lasts like, I think, elements like 5 to 10 years. So it really depends on the application the customer has, which material is the right choice. But this graph gives you a good overview what we can offer. These are only our standard materials, so for special cases, we even offer other materials. And here's our liner portfolio. This graph is the same idea, but divided a little bit different. The dark orange ones are our barrels if we have a liner inside. There we mainly choose two materials. We have our BQ, which is a construction steel, and we have our BS. If the customer has a very corrosive environment, then we could use BS for a liner. I think our most used liner is BG, and it fits to very many applications very well. And for applications where the customer really has a problem with corrosion and abrasion, we can choose our BX. I will show you on the next slide a little bit what it is. And we have some customers who are totally fine with AA. This is relatively similar with OO, but a little bit more focused on the abrasion resistance so that the elements wear before the liner or before the barrel. It's the same with BG. It's a similar material to 25, but BG is a little bit more focused that the abrasion resistance is higher. Yes. And then I will show you what's about BX. So BX was a development made by Picard, and it's called Tape Take because that was a project name. And here we have a metal matrix with carbides. So the matrix has a hardness about 50 HRC, and the carbide cannot be measured in HRC anymore. So the 1600 to 2000 HV, that should be around 75 HRC. And there you get a very high wear resistance paired with abrasion resistance. So we could like getting up in the lifetime from one customer, he has like 3 months lifetime before, and with this barrel, I think we get up to 2.5 to 3 years. So it was really adventurous for him. And then we have also our shaft. In shafts, we have different materials, but we use normally two standard materials. We have our DF, which is really our standard. It's an ESR melted steel, which has many advantages because you have a very high purity. And we have a carbonitride surface. That's more for getting or save the shaft because then it's easier to pull up on and up the elements and you have no scratch marks on it. And they have a tensile strength up between 1150 and 1350 Newton per square millimeters. And you can use it up to 450 degrees. From the properties, EG is relatively similar, but this is a stainless steel which is precipitation hardened, and you can use it in corrosive environments. Some customers have very liquid products and it's getting to the shaft and then they have a problem. And in the pet food industry, we really use this material oftenly because there it's very hard to get the elements off when the shaft is rusted. Yes, and here's one last slide about what we can do in our facility. So in our lab, we are able to prepare samples, to do analysis about material and how the microstructure of a material is. We can do investigation reports when something breaks or if we have any problems or trouble. We can do nearly all hardness measurements. And we are able to work together with institutes and universities if our lab has not enough facilities. And I think we have a wide range of know-how to get all these things together. Okay, that was all of me. Thank you for your attention. If you have any questions, please ask. And if not, will Sebastian go further.
Yeah, thank you, Katharina. That ends the segment of our metallurgy. So if you have any questions on metallurgy, now is the time, or if you think of them as Sebastian, I'll get some of the manufacturing segment and what we offer as far as different designs that see if Picard can create for you.
So thank you very much.
And I forgot to tell you that I am your engineering service manager for the US, Kyle Messman. So if you have any service questions or anything about engineering that's offered here in the US, feel free to ask. But I will hand it over to Sebastian now and he'll get started.
Thank you, Kyle. In the next few slides, I would like to show you our capabilities to make customized spare parts, which are provided by CI Picard worldwide. And so I would like to start with conveying element. Maybe you already know this ordinary elements, which are with a standard profile or with an undercut profile, and if they are as provided as a single piece. So we make our here the three profiles as one pieces, and I would like to describe you why we are doing this. If we have these elements as three single piece elements, and you are putting these elements together, you have here, at least at this side, an overlay of these two profiles. So what is the problem with this? If we have an overlay at latest at this point, this is here about at this place, you have here an undercut of your of the profile, and the problem is that there may be your product, the polymer, for example, may rest on this place for a couple of times, and it burns. And at least then the burnt particles will release on this surface and will go into your product and into your melt. And then you have the burnt particles, these little black spots in your product. So many customers don't want this, so we are providing them with this transferring element, which has very good radiological geometry with no black spots or any other flow difficulties with our reducing the flow. So one other transitional element we are providing is where we have transferring from different flights. Here, for example, we are transferring from a two-flighted element to a single-flighted element. The reasons why we are do this is the same like in another element. We want to increase the radiological properties in the configuration. So we also have cleaning blocks which are customized. Here's an example of a cleaning block with so-called shoulders. The modification here is you have a standard cleaning block, but each cleaning block, cleaning disc has a cutout of about 50%. You can see here or here. We are doing this because if customers have a very sensitive product, which where you don't need to put in so much energy in the cleaning zone or melting zone. So this is maybe the solution to not overstress your product. So we do also very special elements. Here's a combination element of a conveying element and a cleaning block with different flights. It's also done as a one-piece solution. That are not 2 or 3 pieces. This is one piece. It's starting with a conveying element. It is transferred to a 2-flighted cleaning block or cleaning disc and goes further as a 3-flighted eccentric cleaning block. So what was the special part? It took some kind of effort to design it. It took more. It was very challenging to produce it for the guys in the production. Yeah. So we are going through the shafts. We are making shafts for the common manufacturers, but also are able to do specific or customer-specific shafts. We are using therefore calculation software called KISSOFT when we are making shafts according to the standards DIN 5480 or ISO 4156. But we are also making shafts. Sorry, we also are making shafts manufacturer specific, like this one with integrated 2 round phaser keys or hexagonal shafts. We are also able to make calculation to give our customers an information about the estimated torque load. So you have the safety that you can run our shafts on your process. Yeah. Also, as a service, we can do is to create a configuration. And we are doing is this often as a service for customers for their own documentation. And often when you do this configurations, we use a modification of a configuration. That means that we are not only replace some elements with another elements or displace some elements and looking how it's improving or checking what's an effect on the process. We are also can take a look, okay, where you came from, what we receive, and what do we have to do to get improvement on your process. Yeah. Further, we do also customizing barrels. We don't only make refurbishment of barrels, we also can transfer solid barrels or barrel housings into barrels with liners. So you can see here on this example, we have an old solid barrel. In our production, we are cutting with wire ADM this old paper out, make an oval contour, and then we can place a new liner in the old barrel, and you can put it again in your extruder. So, as a further process, we can do some modifications on a cooling system. For example, if you have an single loop cooling system like shown here, and you need more cooling power, or you have issues with overheatment, we can modify your barrel with this cooling system. Of course, we cannot modify existing barrel. We need to make a new barrel due to the very different geometry. In the next slide, I would like to show you an example what we've done a couple months ago. What was a very special project for us because there were many challenges to do, and we did this project hand in hand with of course, with our customer, but also with many other departments at CA Picard and with our suppliers we are working with. So what you can see here is an integrated liner. We did this because our customer don't wanted a liner like this one. He insisted that he wants an integrated liner with our BG material. Sorry. The challenge here was not only to make this liner by hipping. There was always a challenge to make the hardening of this liner, of this lining, because we have, if you can see here, this solid liner is not is very massive. We have a lot of volume of material. So while we were hardening, as Katharina said, we want to make a very fast cooling. But when we cool down this liner, sorry, if we have cooled down this barrel, there's many worms what is saved in this material. So we had many calls with our heating supplier, how we make this cooling fast enough to get the hardness into this coating. There was another challenge we have to do. That was the cooling system. The usual used cooling system in this barrels was the single loop cooling system like here, but we cannot do this in this case we had because this cooling system is usually welded on the front side. So the problem is if we would weld it here, we have again an influence of worms because of the welding process. So we had a bad impact on our layer. So we had to modify the cooling system. We made this one. Here's a partially cooling because we don't have to weld it. We can close this here with some expanders. So we did this project not only for one barrel. We did 6 barrels. So we gained a lot of experience in this and a lot of gray hairs. So this is one product we are also providing and modifying for our customers. Some customers are using the die plates as the last part in the extrusion process, and some customers are asking us to modify this, especially for in the amount of the bow holes. In this case, we should do transferring this die plate from 35 holes with 5 millimeter diameter, 5 millimeter of diameter to 60 holes with 3.2 millimeters. So the challenge here was that we could not put 60 holes in row in this because they are too narrow to each other. If you can imagine, if we're pressing the polymers through the holes, they would glue to each other, and you cannot cut the polymer into granulates anymore. So we decided to make a 2-road design to gain more space between the holes, and the 60 single strands go to this granulator and could be cut fine into the granulates. Yeah, in general, at CA Picard, we don't have departments which are really working on their own. There's always a co-working between all departments. So the design department is working with the research and development. We are in connection with our production, for example, for special material requirements. So also we are doing assistance in technical communications for internal as external suppliers, and we are a lot of networking with universities and other partners. Yeah. The R&D in our house is a main department from projects. We are often have the project leading, and we are assisting our colleagues from the sales. For example, yeah, projects from beginning from the customer request up to production. So at last, I would like to show you our new service. We started a couple months ago with simulating. Therefore, we have bought simulating software called Sigma. This is simulating polymer processes for co-rotating screw extruders. As you can see here, at first we are building up the configuration at the customer side with the screws and kneading box, for example, and also the barrels. Then we are putting some machine data like input power and screw rotations. Also, we are putting in information of the polymer you are producing. So after we got all this data, we get the result as a diagram. And for example, if a customer is not satisfied with his through output, we can change the configuration and see how this configuration has an input on here, for example, for his on his output. So this is a process that goes always hand in hand with the customer, because we are the simulations, the solution of the simulations are very depending on the information we get from our customers regarding the machine data, especially regarding the material data. This was all from my side. I thank you very much, and if you have any questions, I'm happy to answer them.
Yeah, thank you so much, Sebastian. Katharina, great
You're
job.
welcome.
Thanks for joining us all the way from Germany.
We're happy to be here.
Yeah, we are very happy.
Happy to have you guys. I think Guy might have a few things to close us.
Yeah, just for the people that attended this presentation, the goal of this was just to let you know that we're not just a company that makes elements, shafts, and barrels. We have a lot more to offer. We have a very, very deep and historic knowledge of metallurgy, and we have a lot of very skilled people on our staff that are willing to help you with custom designs, reducing abrasion, corrosion, anything that you are dealing with. We also have a full service department that can come and do barrel inspections and provide you with a very deep report with respect to that as well. So we want you to know that we're a valuable supplier, and we have a lot more to offer. And if you have questions or thoughts about this presentation you saw today, contact any one of us directly or reach out to your regional sales manager in your area, and they'll be happy to help you. So thanks again for joining us, and have a great rest of your afternoon and a wonderful weekend. We'll talk to you later, guys. Thanks for you guys in Battle Creek. Thank you so much for everything you did here today.
Okay, thanks, Guy. I think we got one question. Question is, how do you offer a design software that covers parts and machines from multiple OEMs and their elements?
Okay, if I got your question right, so the answer is, I think no, we don't have a software which covers this elements of other OEMs or competitors. We have our own CAD software, so we have our own database of element designs from different OEMs.
Yes, and we can give them into the simulation software.
Yeah.
So we cover all elements that we have made or that have designed. So I think then we will not sell the software, we're just using it in-house.
Yes, yeah, we have a university library, universal library.
Yes.
Many universities have
Yeah.
poured into the database for the signal.
And we can put them in by ourselves because we know the design.
Yeah.
So
Yeah.
I don't know if that answers your question or not. Yes, it does. Thank you. Okay,
You're welcome.
excellent. Well, if we don't have any other questions, thanks again for joining us today. We really appreciate it and excited to be able to offer this webinar for you guys.
thanks a lot.
Thank you very much.
Take care.